If you remember, we ended the most recent lesson by asking the question, is there a better method to approximate functions instead of using the calculator? And the answer is yes, there is. Otherwise, we wouldn't have gone through all of that detail in generating the series for sine of x, cosine, and e to the x. But nevertheless, here we are at Taylor's formula. And if you remember way back when, in Algebra 1, you learned how to solve quadratic equations by square rooting both sides, and then also factoring both sides, and then completing the square. And after you did all of that work, you learned that there was one formula that could help you solve any quadratic equation as long as you knew what the a, the b, and the c were, and that would be the quadratic formula. Well, similar to how we've generated series, if you can remember, based on using the template 1 over 1 minus x. We've used differentiating both sides of an equation which would involve one common function on one side and the series on the other side. So differentiating both sides, integrating both sides, and the most recent lesson was grind it out, and again, that was temporary, and that's what we did. We grinded it out. So there's that grinded it out. Whatever, you understand. But now we have a formula, and again we call it Taylor's formula. Okay, so let's take a look. F is a function such that f and its first n derivatives are continuous on the closed interval from a to b, and then the n plus first derivative exists for all values of x in the open interval a to b. Then there must exist a value. So this is a lot of talk about this, you'll start becoming more familiar with all of what that means. But here's the formula, and I want to point out a couple key parts of that formula. Okay, this looks really, really similar to what you've done before. We have b, which is the value of x that we're going to try to approximate f at. So f of b, just like when we did, I think it was the sine of 4, we did sine of 4, where b would be 4. So f of b would just be a specific value of x that we want to figure out an approximate value for. And then the a is all throughout this entire formula. So you can see an a everywhere. Well, what is a? Well, a is where the polynomial is centered. Okay, we have to have a starting point for the polynomial. So we have a function like the sine of x, and we've started the function. So let me draw that picture up here. So here we have 0, we go 0, 0, we have sine of x looking like that. And we've built our polynomials right there at 0 when we did y equals x, and then we did y equals x minus x cubed over 3 factorial, and so forth. We built them or centered the polynomials right there at 0. But a implies that we could actually center a polynomial anywhere. The a here is 0, but if we decided, well, we don't want to center it at 0, we want to center it at x equals pi, or a equals pi. So we could center the polynomial at, I think I said pi, but at 2 pi. So we could center it at 2 pi. We could center the polynomial anywhere, and that, again, just kind of like a home base for the polynomial. Okay, so we've got that. B represents, again, the value of x that we're plugging in, and so we can see here we have a polynomial here, an nth degree polynomial, and then we add to that this kind of big ugly mess here that I highlighted. This right here is called the error in the approximation, because when we're approximating, we're going to get close, but then there's going to be some error. Now you might ask, well, why don't we just know the error? Well, if we knew the error and we knew the approximation, then we could add them both together and get the exact value. But that's not what we're able to do with an infinite series. We're only able typically to get an approximation, and then we can get a maximum value for an error, and we'll talk about that in a little bit. Okay? So basically, here we have f of b, so the function down here, f of b is approximately equal to this nth degree polynomial. And as we've talked about before, by increasing the number of terms, we can improve the accuracy of the approximation. Taylor's formula gives us the first n terms of the series. And so keeping in mind, our key question would be, what is the series? Well, guess what? Just to reiterate, this formula can generate the terms of a series, okay? The first n terms of the series, okay? And then we have this error bound. So like we said, this big ugly mess here highlighted is the error in the approximation. And what we really want to find is, well, how big can that error be? Because that's an important thing. How good is our approximation, or how large can that error be? And that would be what we can talk about right here. Okay. So we're going to predict the error, and let's look at an example. So use the 5th degree Maclaurin polynomial. Okay, so there's some new terminology here. I think we may have talked about it a little bit earlier. A Maclaurin series is a series that's centered at 0, but it's a Taylor series centered at 0. Oh, and it says that right here. Okay, so the Maclaurin series is a Taylor series centered at 0. So as soon as you see the name Maclaurin, you know that where the series is centered is 0. So we can approximate e to the x by using this 5th degree polynomial here. And if we substitute in 2 for x, we get e to the 2nd power is about equal to 2 for all this stuff. And if we plug that all into the calculator, we would get 7.267, okay, rounding to the nearest 3 digits. Okay, so we're going to take a look and see, well, how does that really actually fit within our boundary? Okay, so that's 5th degree polynomial. We can generate those terms using the Taylor's formula, and that would be a pretty easy thing to do, which we will do in class. Oh, you know what? I did remember one thing. I didn't mention this, but I saw a little typo in there. Make sure, go back to the Lagrange error bound. Make sure that your denominator is the n plus 1 factorial. Okay, it says it up here, but then again there was that typo there. So it's n plus 1 factorial. In class we'll talk about that z. In fact, I think I'm going to cover that next part of the video here. In fact, I'm going to make a brand new video for the last page.